All righty, let us get started then. So today we are going to continue our discussion of latent heat as it pertains to calorimetry. Last time we found out how to add in to our equations the fact that certain materials, as you change their temperature, could change their state, their phase. Big example, of course, being ice. If you put ice in a hot liquid, the ice will heat up, get to its melting point, which is 0 degrees Celsius. It can melt, and then that melted ice can now heat up to whatever the final temperature of the system will be. And we found out that that part of the transition for the ice where it's melting is unique because here you have a part where you're adding energy. Of course, ice won't melt on its own. You have to heat it up. So you add energy into the ice when it's at its melting point. And that energy goes into melting the ice, but it doesn't change the temperature of the ice. So you add a whole bunch of energy into the system. It melts it, but it doesn't change the temperature. So the original equation we had to work with, which dealt with specific heat, Cm delta T, obviously that can't take care of it because that requires a change in temperature. So we needed a new term to go into our equations, which would take care of how much energy is going to be put into the system purely to change the state, no change of temperature. And of course, that was Q is equal to M times L, where M, of course, is the mass. How much of this material do you have? And L is what's called the latent heat. That is just like specific heat, particular to a material. Each material has its own value. And of course, for instance, with water, the latent heat of water to go to ice or ice to go to water, that's a particular number, 334,000. But then water can also boil, or steam can condense into water. So there's a separate latent heat, which is to boil the water. And so what you may see sometimes is what's called the latent heat of fusion, and that is melting / freezing. So this is the value you would use when you're melting ice or you're freezing water or any other material, melting the material or freezing the material. And then a different latent heat called latent heat LV, which is latent heat of vaporization. And this is the number for boiling / condensing. So you may have a problem where you put a pot onto the stove and you put some ice into the pot and you turn on the heat. Well, you're going to add heat to the ice to warm it up till it gets to the melting point, Cm delta T. Then there's going to be the amount of heat required to melt that ice. That's called the latent heat of fusion. So you're melting the ice into liquid water. Then that liquid water will heat up to 100 degrees if you keep the heat on. That's Cm delta T again. And then once water gets to 100 degrees, now it can start to boil. So that's a different change of phase. Now you're going from liquid to gas. It's not the same as solid to liquid. So there's some other number, which is called the latent heat of vaporization, which is the number you would use if the water is going to boil into steam. Okay, so just to let you know, if you're looking up in a textbook or you're looking at other problems, you may see two different latent heat values for water or whatever. Just know that's what the difference is. Latent heat of fusion, that is solid to liquid, so melting or freezing. Latent heat of vaporization, that's the easy one to remember. Vaporizing, you're turning a liquid into a gas, or vice versa, gas back to liquid. But again, all these values on a homework problem or on a test problem, you'd be given these numbers, unless it's the thing you're actually trying to calculate in the problem. You don't have to memorize any of these numbers. All right, so what we'd like to do today is work a couple of examples and just get a little bit more used to it. Of course, don't forget, and I'll try to remind at the end of class, we have a homework assignment. I think it's due tonight, 11:59 p.m. It's on Canvas. It's calorimetry homework 1. So it's a problem on calorimetry that just deals with CM delta T stuff. No latent heat on this particular assignment. So if you haven't worked on it yet, be sure to do so. Obviously, it's due tonight. And I will be posting the second homework on calorimetry, which deals with a latent heat problem as well. So I'll email when that's posted. All right, so let's do an example. So here's an example, a little different than what we did last time, but it's still the same type of problem. The problem says you have a half a kilogram of ice at -8 degrees Celsius. If you add 250,000 joules of energy to this ice, what will be the system's final temperature? Okay. So calorimetry problem, we're dealing with certain materials, we're adding energy or energy is being transferred, and we want to know something about how the temperature changes. Now, this is a little different than previous examples because usually previous examples, what you have is a container, you put a whole bunch of different materials into this container, mix it all up, and then see what the final temperature is. So you're never really dealing with how much energy is going on. Remember, you start with your Q's, but then you turn Q's into CM delta T. Here, however, we're told exactly how much energy will be given to the system. Okay, so slightly different. Let's see how to handle this difference. What do we do? Well, my thought process when I read this question is I say, look, I know what's going to happen in the system. I'm going to have the solid ice, the really cold ice. I'm going to heat that ice up until it gets to the melting point. So there's going to be some Q, I'm going to call it Q ice. And that's going to be a CM delta T, right? I'm going to add some energy into the ice to heat it up till it gets to the melting point of 0. Then there's also going to be a Q to melt the ice. Right? Now that it's at the melting point, 0 degrees, it can melt and it's going to soak up some energy to do so. So that's going to be an M times L. Now that this ice is melted, it's now liquid water. And that liquid water can keep taking in energy until there's no energy left. I don't know, maybe I used up all the energy already. I'm not sure, but we'll see. So just in case there's still extra energy, I'm going to say, well, maybe there's a Q for the melted ice. That melted ice can heat up to some final temperature, so there'll be a CM delta T for that guy. And so I'm going to assume this is what's going to happen in the problem. Now, of course, maybe it goes further. Maybe it keeps heating up till it gets to the boiling point. And then once it's at the boiling point, it'll boil. So there's another M times L to boil the water. And then now that the water's boiled is steam, that steam can heat up to some final temperature. So CM delta. So I could add more. But for now, let me see how much energy is required just to do this and see if it uses up all the energy. If it uses it all up, I could stop here. I don't have to go any further. If, however, I calculate how much energy is required to do this, and it's less than 250,000, Well, that just means there's more energy there, so I have to keep going. I'm going to keep heating up this water till it boils, and then I'm going to let it go to steam, and the steam can heat up and so forth. So that's my plan. Each one of these steps, I'm going to see how much energy does it take to do each step. I'm going to add up all those energies together and say, I know it has to equal 250,000. So what must be the final temperature for that to happen? So I'm going to say, add up all of these things, and it better be equal to 250,000. Right? That's what the problem's saying. You have some ice, you're adding all this stuff into it. What's going to be the final result? Well, the first step is the ice is going to heat up to 0. That takes a certain amount of energy, maybe 100,000, I don't know how much. Now that it's at the melting point, it's now going to take some new amount of energy to melt. Maybe that's 100,000. Well, I still have some extra energy. So the third step, now it's going to heat up some more. How much energy is required to heat it up, and so forth. So let's see. The first step, Cm delta T for ice. Well, we're going to assume again, I forgot to give it to you, but C for ice, let's say, is 2,000. C for water, I'm going to say, is 4186. Latent heat for ice is 334,000. Okay, so those are your little constants. You may need to do these calculations. All right, so let's do the first step. Q for ice. This is how much energy will it take to get my ice, which starts at -8, up to the melting point? Well, it's C for ice, 2,000, times the mass of the ice. I have a half a kilogram, so 0.5, times the change in temperature. Well, I'm trying to get to the melting point, which is 0, and I'm starting at an initial temperature of -8. And there we go. There's Cm delta T. Of course, the 0 minus -8, that's just +8. So I don't need to worry about all that. You know, it looks worse than it really is. That number is just 8. So I take my calculator, I say, okay, 2,000 times 0.5 times 8, and I get 8,000, of course. So the first step is going to soak up 8,000 joules of energy of the 250,000 given. All right. Next step, M times L. I'm now going to melt all my ice. How much energy does it take to melt the ice? Well, it's M, 0.5 kilograms of ice, times L, the latent heat of fusion, which is 334,000. All right, so calculator, 0.5 times 334,000, I get 167,000. All right, so far I have 8,000 from step 1, 167 from step 2, 167,000, I'm sorry, from step 2. So how much energy is left? Well, I'm going to say I started with 250,000. I'm going to subtract off 8,000 of it from the first step, and then I'm going to subtract off 167,000 from the second step. And what do I have? 250,000 minus 8,000 minus 167,000. I have 75,000 joules left over right now. So that's how much energy I have to give this last step. Okay, any questions so far on what I've done? Before I move on, of course. Everybody following what I'm doing?
Yes.
Yes.
All right, good. So the last step is the harder one. The last step is, look, I don't know what this final temperature is. That's what I want to try to find out, right? That's what the question's saying. What's the final temp? So I'm going to say, look, in this last step, I'm going to have the melted ice, which is water, starting at 0 degrees, and I'm going to let it heat up until it's used up all the last bit of energy, which is the 75,000 that's left. So I'm going to say C for the melted ice. Remember, once you've melted the ice, it's not ice anymore. So now you have to use water, 4186, times the mass. Well, it's still half a kilogram, times the change in temperature. Well, it's final temperature, the thing I want, minus the initial temperature. Well, remember, it's not -8 anymore because you've already heated up the ice to melt it. So now the melted ice is starting at 0. So there's Cm delta T for this last step. And I know the amount of energy that I have to use is exactly 75,000. And so there's my equation. I know I used a certain amount in the first step, take that out of the 250,000. I used a certain amount in the second step, take that out of the 250,000. What's left? 75,000 is all I have remaining. So in the last step, you say, if all I have is 75,000 to give you, how much delta T will you get? Or what will be the final temperature, in other words? And so it's just solving this equation. So we say, okay, well, 4186 times 0.5, that's 2093 times TF must be equal to 75,000. Get TF by itself, divide over the 2093. So it's 75,000 divided by 2093. And I get TF must be 35.8 degrees. And there we go. Given a certain question.
You have to use the 2093 water 4186 times 0.5.
Yeah, so the 2093, that came from 4186 times 0.5 times TF. Okay, so I just multiplied the 4186 times 0.5 times TF, and that gave me 2093 times TF. And on the right side of the equation, of course, is how much energy do I have here, this Q, to be able to use? And of course, I know that based on the fact that the first step used that much, second step used that much. I started with 250,000. So what's left over is only 75,000 left. So 2093 TF must be equal to 75,000. Divide 75,000 by 2093, and you should get this number. Okay, so does that make sense?
Yeah.
Now, one thing I can do is look at the answer to see if it's right, or not if it's right, but at least if it kind of makes sense. Remember, I said I arbitrarily stopped at Q melted. I have no idea if it's 2,500,000 joules. That's a lot of energy. Maybe that's enough energy to boil it. So maybe I needed another Q to boil and another Q for the steam to heat up. So how do I know if I stopped at the right place? Well, to me, what I would do is I'd look at this final temperature and I'd say, okay, is this final temperature in the region where it's still liquid water? In other words, if the final temperature I got was 110, well, I know something's wrong because I know what I have is water. I've already melted the ice, so it's water. And I know water can't get to 110. So if it got to 110 in my calculation here, that tells me, oh, okay, that means this water wanted to boil. So add in an extra Q for Q boiling, and then you can go from there. Or another thing is, how do I know I had enough energy to melt the ice? Maybe there wasn't enough energy. Maybe I only started with 150,000 joules. And obviously it took 167,000 just to melt it. Well, what would have happened is when I calculate this delta T, this change, this final temperature, it would have been something less than 0. And so that tells me, oh, okay, so obviously I didn't have enough energy to actually melt it all. So I should have stopped at the second step. I would have said, there's not enough energy here to melt all of the ice. So only some of the ice would have melted. Okay. Those are like the really extreme types of questions. That's the kind of question where if you have a professor that likes to trick you on a test or give you a test question that's nothing like the homework problems you've been working, that's what they would do. They would give you a problem that looks like what you've been doing, but there's not enough energy there to actually melt all the ice. And you've never seen a problem where you didn't do that. So you don't have to worry about that for my problems because I'm not trying to train you to be master calorimetrists. But just know that this type of issue occurs. And you see it all the time. If you ever go to a restaurant and you get, a glass of Coke or iced tea or water and it's got ice in it, well, of course, the water was warm or at least room temperature or whatever, and then they put ice in it. Well, that ice heats up and some of it melts, but not all of it melts. And so that tells you there are times where there's just not enough energy in the system to fully melt all the ice. And so that can occur. And if you don't look out for that type of stuff when you're doing this type of work, then you could get false answers. You say, oh, I think it should get to this final temperature, but in actuality, there's no way it can because there was never enough energy even to melt all the ice, much less to heat it up past melting. Okay, so just as an aside for your information, that's something that can occur, obviously. But for us, likely, unless when I'm making up a question, my mind goes blank, I'm going to make the question where it's a straightforward, just calculate this stuff. And in this one, you have something slightly different than the rest of our questions, which is why I wanted to show it to you. But really, it's the same deep down. You have some material, energy will be transferred to the material, and you want to know how things end up. In this case, you have something that can melt in your system, so you have to worry about both Cm delta T and M times L. Also, in this case, you're told how much energy is in the system. Other problems, you're not told. All right, that's no problem. So I'll just say, if this is how much energy I have, each step, calculate the amount of energy that step needs and subtract it away and just keep subtracting it away till you're left with no more energy. And that's where you stop. So that's how you would handle this type of question. You're still using the same equations, still working it out, but it looks a little different. Let's try another example. All right, let's say you have 1 kilogram of ice at 0 degrees Celsius in an aluminum cup whose mass is 250 grams. Oops. You pour, let's say, 750 grams of boiling water into the cup. What will be the final equilibrium temperature? And again, just some pieces of information. C for ice, we'll use 2000. C for water, we'll use 4186. C for aluminum, we'll use 300. Oops. And latent heat of fusion, that is to melt or freeze, will be 334,000. All righty, so there's the problem. Now, what I'd like to do is I'd like to go ahead and give you a couple of minutes to try to work this out yourself before I do it. See if you can get the answer, see if you could work through it, or if you're kind of understanding where you're going. If not, don't worry. Like I said, I'm going to work it myself too, but I want to give you a chance to try it before you see me do it. So take a few minutes, try to calculate this out. Remember, you're looking for the final equilibrium temperature of the system, the final temperature. You have ice, it's in an aluminum cup, and then you put hot water into the cup. Of course, boiling water boils at 100 degrees Celsius, in case you forgot, and you want to know the final temp. Okay. Question.
You know, when you're doing you know how you have 4 of the different given portions of the problem. So is that how we're supposed to know how many different is it quantum? The Q equals C delta T. So that means we're supposed to have 3 of those and 1 of the latent heat problems. That's how we're supposed to know how many it's going to be.
Not necessarily. That's a good question, but no. This is all the data you might need, but maybe you might not need. And in fact, if this were a test, I'd probably have at the top of the first page all of these little quantities. And some of the problems don't use them, some of the problems do use them. So this is just information for you to have if you need to use it. Now, how do you know how many Qs to have? That's the part that you're trying to understand. That's the part you're trying to figure out with your intuition. As you read the question, what you want to do is picture in your mind, okay, each part of my system, well, I've got ice, I've got a cup, and I've got boiling water. For each one of those, what's going to happen? For instance, the boiling water, I can do that one. Well, the boiling water is going to go from 100 degrees and it's going to cool down because you're putting it in ice. So if it's a cooling down thing, that's a Cm delta T. So one of the Qs is Q for water, and that's going to be Cm delta T. And then you say the same thing about the cup. What's going to happen to the cup? Well, maybe it heats up, maybe it cools down, whatever it is for the problem. And so there's going to be a Q for that guy. And then what about the ice? Well, you can heat up the ice, you can melt the ice. Now that it's melted, all of that stuff. Those are the things you ask yourself. And for each one, you'll have a Q. Okay, so deep down, that's the physics of this problem. Everything else that comes after that is just the math. Okay, well, that's math. Physics is looking at this question and understanding what's going to happen and trying to picture what will happen. And then using that picture in your mind to tell you what the equation will look like. How many Qs am I going to have here? Each Q, is it a Cm delta T or an M times L? Okay, that's the essence of the question. So no, don't look at how many constants I give you over here in the green box and just assume each one of those is going to have a Q associated with it. Sometimes that's true, but sometimes it's not. Maybe one of them you don't even need in this problem, or maybe 2 of them you don't need. Okay, I gave it to you in case you need it, but don't make the assumption you have to use everything. Okay.
So would it be safe to say that in this one, the aluminum cup would be one of them that, because it's not going to affect the final equilibrium temperature?
Well, remember, usually the way I handle my problems is if I'm going to put a vessel in the question, I'll use a metal cup if that cup can change temperature. So then it is important. And I'll use styrofoam to say it's not going to change temperature, so you can ignore it. So for this problem, the fact that it's an aluminum cup tells you, that cup can change temperature, so it will soak up some energy or give off some energy depending. So yeah, the aluminum is important here. So again, take a few minutes. Anybody that gets an answer, go ahead and type it in chat. That way, at least I can see kind of how far along we are. So I give you enough time to actually work on it before I start doing it myself. So.
I have a question. Would water be included in the queue for melted ice?
Do you think it should be included?
I don't know. Yes?
Well, let me ask you this. If the ice has melted, what is it now?
Water.
That's right. So, and that's the thing you're going to do CM delta T on. Even though it came from the ice, it's now physically water. So you should use the specific heat for water because that's the thing trying to heat up now. So good catch, definitely.
Can I still use the mass of the boiling water that we added in with the water that was melted from the ice?
Here, what I would say is because we're separating each piece from each other, I have something for the boiling water over here on the side. That's Q for the boiling water. So that takes care of him. So over here, I have the ice stuff. I have Q for the ice, let's say, a Q to melt the ice, and a Q for the melted ice. Well, each one of those is all dealing with ice by itself. Technically, the melted part, as you just said, it's now water, not ice. But the only thing that affects is which specific heat. The amount of that much water is however much ice you started with. So what you should do is, even though, yes, you're using the specific heat of water in this part, you're still talking about the thing that was ice. So the mass associated with it is still the mass of the ice. Okay, so does that make sense?
That makes a lot more sense. Okay, thank you. And then we also add in the Q for the aluminum cup.
If you think the aluminum cup changes temperature in the problem, then certainly.
Okay, thank you.
Sure.
I got a question. So for boiling water, is the specific heat is the same as you already put for just water in general?
Yeah, I called it boiling water just to let you know it's at 100 degrees, but I'm not actually going to boil it. So you're not going to have an M times L to boil the water. or to steam or something like that. So when I call it boiling water, what I mean is it's water that's at 100 degrees. So it's still water stuff. Okay. Does that answer your question?
Right. And there's okay.
All right, I've started getting a couple of answers so far. Let me give about 30 more seconds, only because we're nearing the end of the class. And then I'll be able to try it out myself. And we'll see if we match, or if not, where either you went wrong or maybe I went wrong, because that's a possibility too. But a few more seconds and then I'll go ahead and try it. All righty. So I'll go ahead and try this. When I read the question, I say, okay, we've got some ice. We put it in a metal cup and we're going to put some hot water on it. What are all the important things that are in my system? Okay, first of all, the ice. Well, generally speaking, you can have Q for the ice. And this term, remember, is to heat up the ice to its melting point. Then there's going to be Q melt. Once it's at the melting point, this is how much heat to melt it. Then Q melted, as I call it, is now that it's melted as water, that water can heat up to whatever final temperature we need to get it to. So that's everything that could possibly happen to the ice. We've got the boiling water. Okay, the hot water, that can cool down because you put it in some ice. But that's just Cm delta T, so there's a Q for the hot water. And then, of course, all of this is happening in a metal cup, and metal, of course, can change temperature. So the metal cup itself can also have a Q. So generally, these would be all the Qs that could be in this particular problem, set it equal to 0. Now, this problem specifically, however, is pretty nice because one of these terms I don't need. And the one I don't need is this one, the first one. The reason I don't need the first one for this problem is because the ice already starts at 0. So if it's already at its melting point, I don't have to heat it up to the melting point. So if I were to do Cm delta T, let me Cm delta T for this guy, his final temperature better be 0 because that's where we're trying to get the ice to, but his initial temperature is 0. 0 minus 0 is just 0, so that term is 0. So in general, we need the term if the ice started at -5 degrees or something like that. But here, because the ice was already at 0, I can just forget it. Everything else, though, we do need. We're going to melt the ice. The melted ice is going to heat up to some final temperature. The boiling water will cool down to a final temperature. And the aluminum cup will also heat up to some final temperature. Okay? Any questions about that? Because that's the critical part of the question. Being able to know which terms we need is what you have to do. The rest is just plugging in numbers. All right, now that we know what we have, let's replace all the Q's with Cm delta T or M times L. So again, the first term we don't need because we're already at 0 degrees for the ice, he's fine. Second term, Q melt. This is purely to melt the ice, so that's M times L. Next term, Q melted. Well, now that the ice is melted, it's now water at 0 degrees, and that wants to heat up to some final temperature, so that's Cm delta T. Next term, the boiling water wants to cool down to a final temperature, so that's Cm delta T for the boiling water. Last term, the cup. The cup, you have ice in it, so it's sitting there really cold. Then you put this boiling water in it, the cup will heat up. So that's, again, Cm delta T. And now we have our final equation. These are all the terms, all the variables. The rest is going to be plugging numbers in and solving for whatever the unknown variable is. So let's try it. M times L. Remember, this is the ice trying to melt. How much ice did I start with? 1 kilogram. So 1 times the latent heat for ice is 334,000. So there's the first term done. Next term. Now that this ice is melted, it's no longer ice, it's now water. So the specific heat is 4186 times the mass. How much of this melted ice do I have? I had 1 kilogram of ice, so 1 kilogram. Delta T, the now melted ice is going to start at 0 degrees and heat up to some final temperature, which is what I want to know. TF minus 0. Final minus initial always. So the second term's done. Third term, this is the boiling water. So it's water, 4186. The mass, how much boiling water did I have? 750 grams. But of course, grams is bad. I need kilograms. So it's 0.75. Final minus initial temperature of the boiling water. Well, it starts at 100 because it's boiling, and you put it in this cold cup. So it's going to cool down to some final temperature. So final temperature minus initial, which is 100. So the boiling water term is done. Final term is for the cup. Same exact way. Specific heat for aluminum, 300. What's the mass of the aluminum cup? I'm told it's 250 grams, so it's 0.25. Final minus initial temperature. Well, for the cup, remember, you started with the cup and the ice in the cup. So this metal cup is probably really cold. It's at the same temperature as the ice. However, once you put the boiling water in, that cup's going to heat up to the final temperature. So it's final temperature minus his initial, and his initial is just 0. Same as the ice, because remember, the starting point for the cup was you had the ice in the cup. So the cup and the ice are the same initial temperature. Then you put the boiling water, and that's going to heat it up. So those are all your terms, and you set that equal to 0.
Where did you get the 100 for the initial temperature on the water?
Yeah, that comes from the fact that I called it boiling water. And the boiling point for water is 100 degrees Celsius. Okay, so by calling it boiling water, what I'm really saying is you pour 750 grams of water whose initial temperature is 100 degrees. Okay, so freezing water is 0, boiling water is 100. Okay, so it's kind of hidden in a way, but it's stated that it's boiling water, so that's supposed to let you know, it's 100 degrees water. Okay.
Thank you.
Sure. All right, I know the class is technically finished. Let me quickly get these numbers just so we could get a final answer. So we get our calculator. We say, okay, the first term, 1 times 334,000. Of course, that's just 334,000. The next term, 4186 times 1 times TF is just 4186 times TF. The second term, 0, you don't need it. Next, 4186 times 0.75 times TF. So I get my calculator. 4186 times 0.75 is 3139.5 times TF. And then 4186 times 0.75 times negative 100. 4186 times 0.75 times 100 gives me minus 313950. Okay, so there's that term. And then the final term, 300 times 0.25 times TF. So 300 times 0.25, that is 75 times TF. And there's all the numbers. At this point, what do we have to do? Collect all the TFs together, and all the other numbers, we shift to the other side. So we say, okay. 4186 plus 3139.5 plus 75 gives me 7400.5 times TF. And then we have 334,000 minus 313,950 gives me 20050, all equal to 0. Okay. Let me make sure everything's all right. Mhm.
I ran into that too, because I was gonna ask you, could you have a negative number in this type of situation?
Yeah, that's exactly what I'm looking at here. And it could just be the numbers I've chosen because I just made the question up in my head. Might be exactly the thing I was talking about with the last example, where maybe there was not enough energy to melt all the ice to begin with. In other words, it's possible that I had so much ice placed in this cup that the amount of boiling water I put in it couldn't melt it all. Because as you can see, in case for those of you that don't see what the problem is right now, if I want to solve this for TF, I'm going to get 7,400.5 times TF equals minus 20050. And if I divide that over 7,400.5, I'm going to get a negative number. I get TF is negative 2.7. Well, this immediately puts off warning signals in my head. How is this possible? How am I getting a negative answer here? Okay, there's two ways. Obviously, this is wrong. You started with ice at 0, you put hot liquid in it, it can't get colder. So the first way it can be wrong is I made a mistake in my math. Maybe after I plugged all the numbers in and I multiplied things through, maybe I forgot a negative sign somewhere. Maybe I plugged the numbers in incorrectly. Something may have happened. And so I'd go look to make sure all the numbers are correct. If I go back and look at all my numbers and they are correct, and I'm still getting this weird answer, then the fault lies with the person that gave you the problem. Because they may have told you, like I said, you start with a kilogram of ice and you add 750 grams of boiling water. I just gave you too much ice. So what this answer is telling me as a physicist is I know it's bull crap. It doesn't actually get colder when you do this. So the fact that I'm getting an answer that makes no sense, and I know I did my math correct, means the problem itself is flawed. And I assumed I melted all the ice, but I know I didn't. I could not have melted all the ice because maybe I had too much ice or the original water wasn't hot enough or whatever the case is. Okay. So I'm glad I did this completely by accident because it shows you when you get an answer, you should think about the answer. Does it make sense or does it not make sense? Now, I still need to go through, and I will for next class, I'll go through and make sure my math is correct because maybe I didn't make a mistake. But if I didn't make a mistake mathematically, and this is the answer we're getting, it's purely because the problem I formulated didn't make sense. I could not have melted this much ice with that much boiling water. And that's just my fault for, making up numbers off the top of my head. Okay. But let's say this happens on a test and I gave this question and this is the answer you're supposed to get and you get it. Well, what I would do if I were you, I'd say, does it make sense or something like that? Not all the ice melted or something like that. You box it, you say, look, I know this is nonsense, but this is the numbers you gave me. So it's okay. Because like I said, it's purely because the numbers I gave were not sufficient to make it perfect. But other than the fact that the answer looks really weird, are there questions about how we solved the problem? Very similar to all the calorimetry problems we've been doing. You have materials, put it in a vessel of some sort, gets to a final temperature, you're solving for something. Some of the things are Cm delta T, others are M times L, depends. Add up all your Q's together, that's the physics. From there, replace all the Q's, plug in all the numbers, and one of those things is going to be your unknown variable. That's what you solve for algebraically. All right, so with that, I think we've done all the calorimetry for the class. Next class, what we're going to do, unless there are questions, next class, we're going to move on to the next topic of thermodynamics, which I think we're going to do what's called conduction. And this is one of the 3 heat transfer methods. So if you're keeping up in the textbook or something, heat transfer is what we're doing. And the first one is called heat conduction. So that's where we're going to go next time. In the meantime, don't forget, first homework assignment for calorimetry is due tonight. So if you haven't done it, definitely turn it in. If you have any questions about it, of course, you're free to email me. And other than that, that's all I have. You're free to go. I will see you on Friday.
I have a question about the homework.
Sure.
So
What's up?
if you place it in an ice chest, is that important for the actual problem?
No, I have to say that because in order for calorimetry to work, you have to make sure that you don't lose energy to the outside world. And so if you put it in an ice chest, then it's all sealed and everything's in that box. Other than that, no, it's not important other than that. It's not like the aluminum cup where you have to keep track of the cup. For an ice chest, it's just an insulating box, so nothing can add heat into the box.
Okay, and since it's like 6 separate water bottles, do you recommend we just do like CM delta T 6 times, or can we multiply whatever number we get by 6?
They're identical. So the easiest way, obviously, is just multiply it by 6 for sure.
Okay, all right, thank you.
Sure.